All right, guys, so let's talk about some radioactive dating. If you remember, we talked about and we looked at fossils and superposition and some different methods that we use to do some relative dating to where we can kind of get an idea of when things are, how old they are, and when they occurred. But to take the next step and really have a more of a absolute date, and when things occurred in Earth and how old rocks are, how old the dinosaurs are, we have to use a method called radioactive dating. All right, in radioactive dating, you got to stop and think about it. We're going to talk about mostly the atomic level here. So we're talking about our atoms. And if you think about an atom, let's talk about, for example, hydrogen. Talk about hydrogen. Hydrogen has, of course, a proton. And in a proton, you remember that it is positively charged. And then we have neutrons, which are negatively charged. And our neutral. Sorry. And then, of course, our electrons, which are negatively charged, and they go around the center of the nucleus. And this makes up our atom. So we end up with protons, which are positive, neutrons, which are neutral, and, of course, our electrons, which are negatively charged. We can get into the details as to why that works and how that happens, but that's really for your chemistry class. We're going to actually try to apply this in our earth science classes, or especially our geology. With the atomic number, let's take a minute and take a look at the atomic number so we can remember what these are. If we look at the periodic table, the atomic number is, of course, up there in the corner. If we look at carbon, and carbon is, of course, in the periodic table right here. And when we look at carbon, the atomic number is 6. Now, when we go back and look at it, the atomic number is an element that identifies that number, and it's equal to the number of protons that an atom has. So, if we look at carbon, it has number 6. That would tell us that carbon has 6 protons. And typically that goes along with the electrons as well. So 6 protons, 6 electrons, which is normal. And carbon's a good one to use in this case. And you'll notice I'll talk about carbon a lot because we use a lot of carbon in radiometric dating. Now let's go back one more time. The mass number. This is the sum of the number of protons and the number of neutrons. Okay, so when we look at the atomic number, or the atomic mass, we have the atomic mass right here. It's easy for me to figure out how many neutrons we have in an atom if I take the mass, and in this case it's about 12, some change, but we'll just use 12 for easy math. And then the number of the atomic number, which tells us how many protons. If I take that number, try it again, and I subtract them, of course this gives us 6. That'll tell me how many neutrons I have. So you should be able to figure out, generally speaking, how many neutrons and protons almost every element on the periodic table has. Okay, and along with the number of electrons. Now, that's important to keep in mind as we start talking about radiometric dating. Okay, that should have been a review, I hope. All right, when we use radiometric dating, what we're looking for is actually an isotope. And an isotope is a variant of some parent atom. So, and the parent atom is a parent atom that would happen naturally that is naturally occurring in nature, and we find on the periodic table. So in this case, we're going to talk about hydrogen, the very first one on the periodic table. And you see that it has 1 proton, okay, and it just kind of is what we call protium. Protium is by itself. Now, when we add a proton and a neutron, this is another type of hydrogen and becomes deuterium. Then we'll take another step, and if we actually have 1 proton and 2 neutrons in this case, and they all form this way, we end up with tritium. Now, there's very different in these. They're all different, but they're all hydrogen. So we have hydrogen with 1 proton, deuterium with a proton and a neutron, and of course, tritium with a proton and 2 neutrons. These are all isotopes. Even though they're hydrogen, they have formed differently and become a little different. That's what we use in radiometric dating, radioactive dating, is we're looking at isotopes of different elements. Radioactivity, of course, is a spontaneous change or a decay in the structure of an atom. So say we have that tritium, and it's got those 2 neutrons, and we know there's a lot of tritium. We can kind of determine how old something is by how quickly that tritium turns into regular old hydrogen. Okay, so that's how we would use that. Now, there's 3 ways that this can happen. It can happen in something called an alpha emission. And an alpha emission is an emission of 2 protons and 2 neutrons, or an alpha particle, that leaves that particle or that element. The next one is the mass number that reduced by 4, and then the number is lowered by 2. So this helps us gauge kind of like the atom. We'll take a closer look at that in a minute. Next one is the beta emission. With a beta emission, that's an electron is ejected from the nucleus. So it takes one of its electrons, doesn't want it, gets rid of it, and the mass number remains unchanged. That's how we know it has depleted, it has changed itself, but it changes and reduces, and the number is increased by 1. Okay, so it doesn't really lose much there, just it's 1 electron. Next one is the electron capture. Electron capture is when we have this kind of decay occurring, and another particle captures an electron, and that electron combines with a proton to form a neutron. Okay, so this mass number remains unchanged, and the atomic number decreases by 1. So that's the 3 types that we're going to see when we look at electronic dating or radioactive dating. This is a picture of it. An alpha emission, remember I told you we had to have a proton and neutrons, and what happens is the alpha particle emission comes off. As it sends it off, the atomic number goes down by 2, and the atomic mass down by 4. So that actually changes it, and this comes from our parent to our daughter nucleus. Okay, so this changes that isotope. Now remember, it's still the same element, it just changes it, okay, into how it's counting its mass and its atomic number. An unstable parent, and this is very common in nature, is we'll get a beta emission, and it has too many neutrons or a neutron that it doesn't need, so it kicks it off, turns into a proton and gets rid of it. This is a beta emission. The atomic number goes up by 1, and the mass number has no change. Now, in an unstable nucleus, when we talk about the electron capture, it has a proton, and it wants to gain that electron. It gets that new neutron, and it becomes, the atomic number is fewer than 1, and the atomic mass has no change. Okay, so now I know this is a little confusing and maybe a little harder to follow, but with some of the labs that we'll do through this unit, it'll help you clear up this. All right, so when we use radioactive dating, we all have to have a parent nucleus, and that is an unstable radioactive isotope. I don't know why that's happening. And when we have an unstable isotope, so we have to know of one that's unstable with that rock or with a fossil, and it lets us help us do that. And the product becomes the daughter cell. That's the isotope resulting from the decay of the parent. Remember, and there's 3 types of waves. There's the alpha, beta, and the emission. So when those 3 happen, we can use one of those 3 to help us determine that. And then we have something from this called the half-life. And the half-life is the time required for 1/2 of the radioactive nuclei in a sample to decay. So this is how long it takes from the parent to turn into that daughter product, and that's the half-life for half of that to happen. Okay. You can see if I showed it on a graph, and we looked at the number of half-lives, we start off with 100% of whatever that parent isotope is. And then we know that when it changes to 50 atoms of the parent cell and then 50 atoms of the daughter product, so they turn into those 2 different, same element, but isotopes are different. When they change into half and half, and when that occurs, let's say, for example, in this it's 50 years. And then for it to go from 50 to 25, it takes it another 25 years to do this. Okay, and so forth. You can see how the chart would continue to happen in the number of half-lives. So when we end up with 4 half-lives, we end up with 6 atoms of the parent and 94 of the daughter cells, or daughter nucleus. Okay, daughter isotopes. Okay, so they end up then you have 4 half-lives. That's right. So when we see this occur and we count that up, we're able to tell how long it took it for this to decay. Okay, radiometric dating. The principle of radioactive dating is the percentage of radioactive atoms that decay during 1 half-life, and is always the same. However, the actual number of atoms that decay continuously decreases, and that's the comparing ratio of the parent to the daughter and the age of the sample. Okay, so this is what we're using. All right, next one. Some useful atoms that we try to find when we want to date a rock is we want to use iridium 87 that turns into thorium 232. Another isotope for uranium is potassium 40. So these are some of the ones that we try to look for. Here's some other ones we use. A famous one is uranium. Turns into lead, and it takes it 4.5 billion years to do that. That's why when we talk about nuclear waste being uranium and taking so long for it to turn into lead, you can see it takes 4.5 billion years that it's radioactive. So this is what a problem with uranium is. Thorium turns into lead. It takes it 14.5 billion years, even longer. And then potassium turns into argon, and it takes it 1.3 billion years to do that. So you can see how these certain elements will turn into different daughter cells. And notice this is stable. That means that they are able to maintain themselves at this. So argon's a usable gas, of course, and it does it there. All right, radiometric dating. Let's have some sources of error when we do this, though, so it's not always completely perfect, and we want to account for that. It has to be a closed system, has to be required. And to avoid potential problems with that, we want it to be only fresh, unweathered rock samples. So naturally, we would want that covered. If it's something that's been exposed, it changes how long it takes it to decay, it slows it or speeds it. Isn't a good number for us, so we can't really determine it as well. So we want it to be a closed system, something that hasn't been affected by the outside environment. All right, dating with carbon-14. This is the famous one. Carbon-12, if you remember we looked at the periodic table, its natural state is 12, but we want to look for the isotope carbon-14. And we know that the half-life is only about 5,730 years. The other nice convenient part of this is carbon is something we find in living organisms. So when we find a fossil and we find carbon-14, it can help us determine how old that fossil is. Okay, and it's a great tool for anthropologists and archaeologists, geologists. It really helps us determine age of rocks, fossils, mostly because we know how long it takes carbon-14 to turn into carbon-12. All right, the importance of radiometric dating. Radiometric dating is a complex process. It's very complex. That requires precise measurements. We won't go into that stuff and that kind of thing. We will use some of these activities, but we won't be doing that to the extent that you would do in a regular geology lab. Rocks from several localities have been dated for more than 3 billion years. We know that lots of rocks throughout the earth, we've found them. The Grand Canyon is one of them. And some of those rocks towards the bottom are almost 3 billion years old. So this gives us a very good determining of how old the earth is. If those rocks were formed early on in the beginning of the earth, guess what? About 3 billion years old. And that's roughly about how old the earth is. And it confirms the idea that geological time is immense. So this helps us understand that the Earth is hugely old, far older than we can even imagine, far older than man's ever been around. All right, so that's the end of radioactive dating. There's some labs that you're going to do with this, and there's some reading I want you to do with this as well to help you clear up the understanding of radioactive dating, how it's used, why we use it. All right, make sure you take your notes on this. I want you to add any vocabulary that you have not recognized. It's in the back of your chapter. All right, talk to you later.